Together.
You gotta watch it
Why
again.
does it say pause right there?
I don't know.
Oh, man. Okay, well, so, New Orleans ladies, the problem, and there's a couple things wrong in the song, even though those guys are from Louisiana. You said one of them's still famous, right?
Yeah.
Who is it?
Tad Benoit.
Benoit? Bourbon Street runs here, and Esplanade, and actually they intersect. Bourbon and Esplanade, like it says, they walk from Bourbon to Esplanade. I guess you could, you walk down Bourbon to Esplanade, but they intersect. They're not parallel to each other. Okay? Esplanade is the end of the French Quarter on the southeast side, and Bourbon runs from Canal Street, which is one of the really wide boulevards of the world, across. And a lot of people live on Bourbon Street. You probably don't know that, but if you get down close to the Esplanade end, this is all residential down here. All right? There's like houses and all that. One of the oldest bars in New Orleans is somewhere around here, the Pirate Bar. It's one of the oldies. They also, and I'll never remember the name of the street, but as you get to this end of the French Quarter up here away from the river, they were doing some road construction, redoing, and they ran into a cemetery that's long since been covered up by roads and buildings. So they're trying to figure out, what it was left from and how old it is and all that. But they've uncovered a cemetery there. Anyway, it'd be fun for you to visit New Orleans. Go to the Insect Museum, or Insect, I don't know if it would be called a museum, well, an insect specialist, an entomologist. Entomologist.
ENT, yeah.
ENT, entomologist. But if you go to the insect place, they have the butterfly room.
Yeah.
And the butterfly room is like this huge, beautiful room. And it's got butterflies all in it that fly around and land on you and all that. It's a cool place to go, especially if it's raining in the quarter or if it's too hot. And if you go there, if you walk by there at night, and it's late enough at night that it's quiet, and you're leaning up to the window, you can hear all the different insects in there making all the noise. It's pretty cool. Yeah, at night. Now, New Orleans ladies. So what happens is, we have our New Orleans lady, and she is 6 foot tall. Yeah. 6 foot tall, New Orleans lady. Okay. 6 foot tall, New Orleans lady. Now, then we have the light pole in New Orleans with the Doric base and the Corinthian top. Okay. Fleur-de-lis tops. Ooh, Mr. Evans, you can't draw the fleur-de-lis tops. But the Corinthian fleur-de-lis tops with our light. And we'll make it 10 feet tall. Yeah, 10 feet tall. Drawn absolutely perfectly to scale. 10 feet tall. And she's 6 feet tall. Our New Orleans lady. All right? We can make her, no, we can't make her 5 feet tall because it won't work with 10. We'd have to change the height of the pole. 6 feet tall. New Orleans lady, 6 foot tall. And she's walking at night. And she is walking away from the light pole and she's not walking. What does the song say she's doing? She is oh gosh. It only said it a million times. She what by? She sachets.
Sachets.
Yeah, women, New Orleans lady sachets by. She smiles and she sachets by. Well, she's sashaying at 1:30 1/2 foot per second. Okay? So she's sashaying by, and you're down to the quarter, and you're watching her sashay by. And here's what I want you to think about. Okay, I'm standing here, and the light is right there. See the light right there? It shines down, touches the top of my head, it makes a shadow down there, right? What's going to happen when I'm standing out here to that shadow? It's going to come down now, hit the top of my head, it's going to go what? Way out there. So as she's walking away, the shadow's getting longer. Fair enough? Yeah, the shadow's getting longer. So, light comes across here, hits her right on top of the head. She's 6 foot tall. I guess I should have put the 6 on the other side so that you would know it wouldn't be in the way there. Right there, 6 feet. 6 feet. Down here. And then from here to here is her shadow. Only the shadow knows. Only the shadow knows. But as the, what's the word again? Sashays by? As she sashays away from the light at 1/2 foot per second, her shadow is getting longer. Now, I can't call the shadow S because S would look like a 5. I can put, you know. To start with, if she's in New Orleans, well, the good news is she's not walking around the street light. If she was in New Orleans and she was walking around the street light, we might think what? Yeah.
Yeah, she's cracked up. No,
No.
prostitute.
Lady of the evening.
Wow.
Okay?
Yeah.
Yeah. See, if she's walking somewhere, okay, but you know, if she were walking that same little spot, we might think that. Now, but we're going to make her shadow length Y. We're going to make the shadow on the ground Y. And just to help us, we're going to make X how far she is from the pole. So Y is the shadow, and X is how far she is from the pole. And I know the change in X is 1/2 feet per second. And here's my question. How fast is the shadow lengthening when she is 7 feet from pole? All right. And notice I did not put the 7 there because the 7 is what? Changing. Now, if I were going to write this in math speak, there's the English. We translate it to math speak, I would put dy over dt equals question when x equals 7. Is everybody okay if that's the question at hand? Happy with that? So, what is the relationship that ties all the x, y, and all the 6 and 10s together? Not the related part, just the equation that puts it all together.
Well, my guess would be the angle at the end where the shadow hits the ground.
Well, that angle's going to change, but it is, that angle's going to change as she walks.
The 6 to 10 ratio?
Okay,
What about how fast it like?
don't want to do with how fast yet. We just
Or
want-
like how much it's changing based on how far she's going.
Yeah,
Dy dx.
yeah, that's right. We got to have a dx there, but before we can even do the rate part, we need the related part. What formula relates it all together? Then we'll make the rate problem. What formula relates y 610x together? Okay,
Oh, you can do Pythagorean
good try, but you don't need that, because then
Yeah.
you'd have to bring into this length, and we don't
Yeah.
care about that length.
theorem. Yeah. No.
What else do you know about triangles?
And use trigonometry to find
Okay,
You could split it into two triangles.
well, do you see how this is a big triangle?
Yeah.
You see how this is a
That's a
little
little
triangle?
it. Right.
But do you notice that the angle here for the big and little are the same? The
Yeah.
angle here and here are the same, right?
Yeah.
Yeah.
Remember something about triangles that are called blank triangles?
Similar.
Similar triangles.
Yeah, that's what I was getting at.
Yeah, when you said ratio, that's what I was thinking. 6, okay. Y, okay, let's do 6 is to 10. Don't worry about reducing it yet. It's the same as y not to x, though. You can't go y is to x, it's y is to what? X
Y
plus
x
y, or y plus x. It's similar triangles. Now, someone says, Mr. Evans, you know you could have set them up different. Yeah. You could have done y is to 6 as 10. Y is to 6 as x plus y is to 10. You could have done it that way. You could have set up either way. I'm going to go ahead and give you a big hint on shadow problems. Shadow problems are usually similar triangles. I'm also going to give you another hint about similar triangles. You can use ratios for similar triangles. You cannot use ratios for similar trapezoids or any other type of similar shapes. Okay? This only works for similar triangles. Later on, we're going to have a trapezoid problem, and if you try to do it with ratios, it won't work. Okay? So if this ratio system only works for what? Similar triangles. And what do you, anytime you see a shadow, you're going to try to always think first what? Similar triangles. Now, before I work that, I would reduce them. Okay? And I would also go ahead and multiply by the common denominator. 3y plus 3x equals 5y. Then, hey, let's collect the y's all together. 2y equals 3x. I'm going to do a little algebra. I want my y on the left side. It just looks pretty big. Okay? Now, I can now do what? Take the derivative with respect to time. Is that right? So that's going to be 2 dy over dt equals 3 dx over what? dt. And so it's going to be 2 times, I'm off the screen now over there, right? 2 times dy over dt equals 3 times the dx amount, which is what? 1/2. Is that okay? So then I will get dy over dt is equal to 3/4 feet per second. And that's how fast her shadow is getting longer. So the question, the answer to that would be 3/4 feet per second. Now, if I were to work that problem, and I got to this point, and I was out there in the class, I'd probably be just now waking up, and you see where I ended up, so you don't want to do this. But what might you think is wrong with that? What would be a big red flag that something is wrong?
It's faster than the original.
Okay, yeah. I don't know. I'm thinking that Yeah, I'm thinking, well, 6 feet, 10 feet. The shadow's getting longer, right? If you think about it, if I get way out there, that shadow's gonna be really, really, yeah, I don't know. I wouldn't have, that's not the first thing I would have said makes this look wrong. Read the question.
It doesn't say she's moving when she did 7 feet.
We never used the 7.
Yeah. See, that throws students. And I can see why it throws you, because I'm sitting here thinking, wait a minute, I never used the 7. I'll tell you why you never used the 7. Notice when we came up with the relationship right here, that is a linear relationship. Y equals what? 2/3 of x, right? 3/2. Y equals 3/2 of x. It's awesome that I put that on the film. It's the last hour of the day. But y equals 3/2 of x. That's a linear equation. Anytime you have linear equations, your rate of change remains constant. So it doesn't matter how far away she is, it's still going to be what? 3/4 feet per second. You have a linear equation, the rate of change is going to stay constant. This problem can actually be worked without calculus because of that coincidence there. Don't try to do that. Don't look at a problem and go, oh, it's going to be linear. I don't have to use calculus. Don't do that. Go ahead and just work it out. And if it is linear, the calculus is still going to be good for you. It's not going to hurt you. Okay? Is that all right? So, yeah, the 7 throws you, but it's not wrong. It's just a linear relationship. Now, if you were to ask me how fast the tip of the shadow is moving, let's talk about that. Okay, how fast is the tip of the shadow moving? Right here, the tip of the shadow. How fast is tip of shadow moving? Well, I will help you with that one. It's not hard. And I can do it with math, and I can also just help you out right here. Okay, I'm going to use different numbers because I don't want to have to use fractions. Imagine I am walking at 5 feet per second, and I am pushing this out in front of me at 2 feet per second. How fast is the tip moving? I'm walking at 5, and I'm sliding that forward at 3 from me. 8 feet. Yeah, you're going to add them together, right? Yeah. It's how fast I'm moving plus how fast the shadow is getting longer. Well, if you want to do that mathematically, it is pretty easy. The distance from here to here is how the tip of the shadow is what? X plus y from a stationary object. You want to measure for something that's standing still. So the change in the tip with respect to time is equal to the change in x with respect to time plus the change in y with respect to time, which is what I just demonstrated to you by pushing the pole out in front of me. Okay, so 1/2 plus 3/4. So 1/2 plus 3/4, 5/4 feet per second. And again, the 7 has nothing to do with it because it's a linear. I like that problem because it's all about New Orleans. See, gives you a good feeling for New Orleans. Although we did cut off the New Orleans ladies part. Yeah, here's the guy you're talking about right there.
Mm-hmm.
That's him. See, well,
doctor is.
There you go. I don't think a mule is women is lazy though. Maybe crazy, but not lazy.